All right, hi everyone. So today we are going to talk about energy and heating and cooling curves. So before we get into all of the heating and cooling curve stuff, we do have to talk about what the states of matter are. So there are 4 states of matter, but we're really only concerned with 3 in this class: the solid state, liquid state, and gas state. In the solid state, the particles are very compact together. They're still moving a little bit, so they're kind of vibrating and shaking is what we say. Even though they look like they're stationary, they are still moving. They have a very low kinetic energy, though, and they have a very high molecular attraction because they're compact together. In the liquid state, those particles are more loosely packed. They're flowing past one another. They have a little bit higher energy than the solid state, and they have a medium molecular attraction. So you can see that energy's going up, attraction's going down. And then in the gas state, those particles are moving very quickly. They have a very high kinetic energy, and they have a very low molecular attraction. So again, like I said, there's a pattern here which says that basically as the energy is increasing, the attraction between the molecules is decreasing. So I mentioned this term kinetic energy. Now, kinetic energy is just the energy that's associated with movement. So really, the higher the speed of the particles, the higher the kinetic energy. Now, in physics, this is very easy to measure because we can measure the velocity of something and then get its kinetic energy with a formula. In chemistry, it's a little bit harder because these particles are very, very small. So we measure kinetic energy in chemistry with temperature because we know as the temperature increases, the kinetic energy is also going to be increasing as well. Now, potential energy, on the other hand, is stored energy. So this is going to be the energy due to position. Like I said, stored energy. Now, when I'm saying position, what I mean is those chemical bonds. So we store, little molecules store energy within their chemical bonds. So this is the energy that's associated with bonds and attraction between molecules. So this is what a heating curve looks like. You saw a heating curve actually being made with that thermometer in the ice, and then the ice melted, became liquid water, and then the water boiled. So you actually got to see a heating curve actually being made, which is really cool. Heating curves, of course, when you're doing them experimentally, like you saw in the video, they're a little less perfect than something like this one right here, because there's always error in experiments and there's always going to be energy that's going to be lost and things like that. But this is what a heating curve looks like. The main point right here that we wanted you guys to take away from this was look at these plateaus when we have a phase change. This is the most interesting part about heating curves, that when we have a phase change from, say, a solid to a liquid or a liquid to a gas, the temperature of that substance is not changing because all of the energy that's being put in is going toward that phase change. And that's a very, very important part of this lesson. So heating curve, the definition of a heating curve is just a plot that shows temperature changes as energy is added in the form of heat consistently. Now, if we're actually going to label this heating curve, we know that at a low temperature, we have a solid phase. As the temperature increases, that solid is going to melt into a liquid. And then as the temperature increases more, that liquid will become a gas. So like I said, when we go from a solid to a liquid, we call that melting. And when we go from a liquid to a gas, we call that vaporization. You might think boiling, but we do call this vaporization because that liquid is becoming vapor. Now, we can go the opposite way with this and call this a cooling curve. Usually these things are represented on the same graph, but there are such things as cooling curves as well. So instead of heat being added, now heat is being taken away. So the definition of a cooling curve is just a plot that shows temperature as energy is consistently lost, or heat, right, is our energy in this case, and that's consistently lost. So again, we can label our cooling curve. We have gas at the highest temperature, then liquid at a lower temperature, solid at the lowest temperature. When we go from a gas to a liquid, we call that condensation. The gas is condensing into a liquid. And then when we go from a liquid to a solid, we call that freezing. Now, it's very interesting to see that we have this delta H sub VAP on this and delta H sub FUS. This is the heat of vaporization and the heat of fusion. I'm going to talk a little bit more about this later. All right, but this has to do with the energy that is required or that has to be taken away in order to make these phase changes happen. So energy and heating curves. Now, this was the example that I was talking about when you see heating and cooling curves kind of together. So you can see that we have freezing / melting between ice and water and boiling / condensing between water and gas. So usually you see it like this. When we have heating curves like this, there is energy associated here. And we talked about kinetic and potential energy. Now remember, potential energy had to do with the energy in chemical bonds, or in this case, the energy in between different molecules, so intermolecular forces. So when we're changing the state of matter, we're changing the potential energy here. Because remember, the solid had the highest intermolecular forces, the liquid had a lower attraction between molecules, and then the gas had the lowest attraction between molecules. So the potential energy there is changing. So when a substance changes state, the temperature is constant and the potential energy changes. Now, because the temperature is constant as the substance changes state, that means that the kinetic energy is going to be constant as well. Because remember, we measure kinetic energy with temperature. So the higher the temperature, the higher the kinetic energy. But if temperature is not changing, then there's no change in kinetic energy. So the kinetic energy is only increasing when heat or temperature really is changing and increasing. Okay, so kinetic energy changes when temperature changes. Potential energy changes during those phase changes. Now, I talked a little bit about that DeltaH, and that, remember, is the heat that is required or the heat that is taken away during those phase changes. So we have DeltaH fusion and DeltaH vaporization. Now, I'll get a little bit more into the actual sign of this DeltaH, but all you guys need to know about this DeltaH for now is that this is the energy that you need for a phase change. So when you're going from a solid to liquid, this is the energy that is put into melting that solid into a liquid. When you're going from a liquid to a gas, this is the energy that's put into vaporizing that liquid to be made into a gas. Now, and again, when you're going from a gas to a liquid, it's the energy that's taken away, all right, taken out of the system in order to condense that gas into a liquid, or the energy that's taken out of the system in order, I'm sorry, my dog's barking, in order to freeze that liquid into a solid. So you have to take energy away, and I'll get into that in a second. Now notice how we have two different names here. This is the DeltaH of fusion, so the heat of fusion, and the heat of vaporization. Now, vaporization is probably easy to remember. That's the liquid to gas stage or gas to liquid stage, because we know that liquid to gas is called vaporization. And we think of, water vapor and things like that. Fusion is a little bit harder to remember what this term is, and this is, the energy that's going into the solid to liquid phase or the liquid to solid phase. Fusion, I like to think of liquid going to solid. Those particles are fusing together into a solid. So that's how I remember that DeltaH is called the heat of fusion. Now, DeltaH is also called enthalpy. And, we like to have a lot of different names for things in science. But enthalpy is just a measurement. It's just heat energy, really. And so we have heat energy going into the system when we're increasing in temperature, and therefore, going from a solid to a liquid or a liquid to a gas. We have enthalpy, heat energy going into the system. And then when we are going from a gas to a liquid or a liquid to a solid, we have enthalpy or heat energy coming out of the system. So this is a change in heat energy here. Now, like I was saying, I wanted to talk a little bit about the sign of that DeltaH, or the heat of fusion or heat of vaporization. So the sign here has to do whether the process is endothermic or exothermic. So an endothermic reaction, or in this case, an endothermic process, because really this isn't a reaction, we're just changing phases in this case. Endothermic means that heat is being added to the system. And therefore, since heat is being added to the system, then our DeltaH, our heat of fusion or vaporization, that is going to be positive because you're inputting heat. It's positive. So this is like melting or vaporization. I like to think with endothermic exothermic. N is like in, right? Heat is going into the system, and our delta H is positive. Now, with an exothermic process or exothermic reaction, heat is coming out of the system. So in this case, our delta H is going to be negative. We're removing the heat from the system. I kind of like to think of this as like exoskeleton. Have you heard of an exoskeleton? It's like the skeleton outside, so it's coming out because it's outside. That makes sense. That's just how I remember those things. And then this would be like condensing or freezing, because you have to remove heat in order to do something. When you have an ice tray and you fill it with liquid water and then put it into the freezer, that heat has to be removed from the liquid by the freezer in order to become frozen water, which is just ice. So our delta H in this case is going to be negative. So that's a little bit about enthalpy, about heating and cooling curves. Now you guys all know how to label those things, and you know the types of energy that are associated with the different parts of the heating and cooling curves as well.